In this podcast, we're going to focus on section 16.3 through 16.4 in acid-base equilibria. So I guess starting off with water, because most acid-base reactions take place in water, and water is super important when it comes to these reactions. Let's focus on the fact that water naturally kind of breaks down into ions. Now, we already discussed how water is amphoteric or amphiprotic. Basically, in water, there are always a few water molecules that will behave as a base. So one of the things that you'll notice is, let's say this water molecule right here donates a proton, and in that case is what we would call the Bronsted-Lowry acid, and donates a proton, and here's the conjugate base being a hydroxide ion. And then another water molecule maybe behaves as a base and accepts a proton. And over here, we have what we call the conjugate acid, which is the hydronium ion. So in other words, basically, water molecules kind of naturally will accept a few protons and donate a few protons in any typical sample of water. Because of that, we have what we call an ion product constant. And you guys will love this because it looks really similar to the solubility product constant that we've already talked about. So the equilibrium expression for this is Kw, which is going to be your equilibrium constant for water, is equal to the concentration of hydronium ion times the concentration of hydroxide ion. Therefore, ion product constant. And so the special equilibrium constant is referred to the ion product constant for water, or Kw. So another K. At 25 degrees Celsius, Kw is equal to 1 times 10 to the negative 14th. Now, notice there are no units on there, and now's probably a really good time to take a look at your chart of constants and equations and find out where this is, because we're going to be spending a lot of time looking at these equations. So in aqueous solutions, we know that they can be acidic, basic, or neutral. So how, I guess one of the ways we can think of it is if the concentration of our hydronium or hydrogen ion concentration is equal to the concentration of our hydroxide ion, we normally say that the solution is neutral. Now, if they're not, and the concentration of the hydronium is actually greater than the concentration of hydroxide, then we say the solution is acidic. So basically, acidic just means we have a higher concentration of hydronium or protons in the solution. And then if we have a greater concentration of hydroxide ion, then we would say that the solution is basic. And you see a few things down here that look at whether or not they're equal, greater than, less than. But what you'll notice in each case, when we multiply their concentrations times each other, we get 1 times 10 to the negative 14th. So basically what we find is if the concentration of one goes up, the concentration of the other one will go down, but they always are equal to 1 times 10 to the negative 14th, which is your value for we'll go back to this, ion product constant for water at 25 degrees Celsius. Now, it's important that we say this is at 25 degrees Celsius because this number actually changes and more of the water molecules will ionize as temperature increases. So we just always assume that this is happening at 25 degrees Celsius. So let's try this. Indicate whether the solutions with each of the following ion concentrations are neutral, acidic, or basic. Now, just to help you out with this, remember on your equation chart, you have a bunch of formulas. And so one of the things that I want you to do is take a really good look for right now, right here. Okay. And without doing any calculations, just by estimating, if we have an H plus concentration or hydronium concentration of some number times 10 to the negative ninth, that's a really small amount of H plus. So that's probably telling me if the product of these two have to equal 1 times 10 to the negative 14th, probably have a lot more hydroxide. And if I have more hydroxide ions, what do we know about the solution? We know that it is going to be basic. Now, in example B, we see that we have a concentration of hydroxide ion of 1 times 10 to the negative 7th. 1 times 10 to the negative 7th times 1 times 10 to the negative 7th gives you this ion product constant for water, 1 times 10 to the negative 14th. So in this case, we would see that the concentration of hydroxide ion is going to be equal to the concentration of H plus. And so in that case, we would say that the solution is neutral. And then in the last example, we have a really, really small concentration of hydroxide ion. And so we would expect the concentration of our hydronium ion to be much greater. And so we would expect this solution to be acidic. So you can do a lot of these predictions of whether it's neutral, acidic, or basic without doing really any calculations, but you definitely can feel free to plug in the numbers if you want to and calculate the concentration of the other. So here's another example. Calculate the concentration of hydroxide ion in solution. Now, in this one, I actually am asking you to plug in the numbers. So I'm going to go ahead and I'm going to put up the formulas again. And again, you are given in all of these, you are given the concentration of H plus. So what you want to do is you want to calculate the concentration of hydroxide. Take a minute, pause the video, see if you can calculate the concentration of hydroxide using that equation. Now, C is kind of special because you can do a substitution there to figure out what it is. But basically, I think B you can solve without doing any calculations whatsoever. This one you probably could solve without a calculator for A, but go ahead and try it. Pause the video and see what you come up with. So hopefully you tried those. You should have got for the answer for A, 5 times 10 to the negative ninth. And if you think about that, 5 times 2 gives you 10, and 10 to the negative ninth, 10 to the negative 6th. When you add those together, you get 10 to the negative 15th. Because you have a 10, you can lower the exponent, 10 to the negative 14th, to get the 1 times 10 to the negative 14th. Hopefully B, you guessed 1 times 10 to the negative 7th, because if their concentrations are the same, you have a neutral solution. Therefore, they're both going to have the same power to 10 to get to 1 times 10 to the negative 14th. And for C, which took a little bit of algebra, about 7.1 times 10 to the negative ninth. And in that case, if you think about it, if the concentration of hydronium or H plus is 200 times that of the concentration of hydroxide, we would expect the concentration of hydroxide to be something smaller than 1 times 10 to the negative 7th. All right. So pH. So we talk a lot about pH, like in biology and regular chem, but it's basically this method of reporting hydrogen ion concentration. And it's really nothing amazing other than allowing us to look at numbers in a way that where we don't have a lot of really, really small numbers or negative exponents, and allows us to look at pH in a scale of usually 1 to 14, and our brains just kind of deal with those numbers a little bit better. So in your on your equation and constant sheet, you can find both of these. pH is the negative log of the concentration of the hydronium or H plus ion. And then if you take a look, we can see that right down here. And then the neutral pH is 7. Acidic pH then is below 7. and basic pH is above 7. And if we take a look at this chart, you can see, and this would be worth kind of pausing and just taking some time to look at, but you can really see, first of all, the relationship between pH and pOH. If you look at that relationship, you see something really kind of interesting that happens. Also, if you look at the concentration of hydronium ion versus hydroxide ion, you also see a really interesting relationship between those numbers. So if you look down here, you kind of see a couple things that show up on your equation sheet again. So spend some time looking at these numbers. I think you'll kind of see that they're really not that difficult. One of the things you'll notice is if you look at pH, it has everything to do with that exponent. pH of 2, 1 times 10 to the negative 2. A pH of 3, 1 times 10 to the negative 3. A pOH of 13. Concentration of hydroxide, 1 times 10 to the negative 13th. So you start to see these really interesting relationships. And if you think about negative logs and kind of play around with them a little bit, you'll see a lot of patterns. And you're also going to see that there's going to be more than one way to solve a lot of these problems on your practice sheets. Okay, so let's try these. In a sample of lemon juice, the concentration of H plus ion or hydronium ion is 3.8 times 10 to the negative 4th molar. Okay, that's pretty high. So we're looking at something that's acidic, so it's probably going to have a lower pH. Now I'm going to pop up this chart and I want you to think about a couple different ways that you can calculate this, but right away you can see you've got this formula right here. If you plug in the concentration of H, you should be able to calculate pH. And you should get an answer of about 3.42. And what you'll find interesting is that's not really far off from that exponent. And so thinking about that a little bit as we go through and do some of these calculations, I want you to start thinking about some of those similarities. Also, significant digits. This is something you can ask me about later, but 3.8 has 2 significant digits in it. The significant figures in the concentration of hydronium is equal to the number of decimal places you should record in your pH. Something that's kind of unique to pH. Again, you can ask me about that. The second question, a commonly available window cleaning solution has a concentration of hydroxide ion as 1.9 times 10 to the negative 6 molar. What is the pH at 25 degrees Celsius? So again, you can use this to calculate pOH and then plug it in here, subtract that from 14 to find the pH. Try that out, take a minute, pause the video, and see what you come up with. First of all, one of the things you should have asked yourself is, with that concentration of hydronium ion, would I expect the pH to be above 7 or below 7? And with a concentration of 1.9 times 10 to the negative 6, that's a fairly high concentration of hydroxide ion. It's definitely not neutral. And I would expect the pH to be a little bit higher because of that higher concentration of OH ion. And so we get a pH of about 8.28 times 10, or 8.28. And notice they solve for the concentration of hydronium ion here. So just taking a look at that, I want you to go back and take a look at this and think about whether or not you could use this relationship as well to calculate the concentration of H plus and then plugged it back into here. So hopefully you kind of see what I'm talking about. There's going to be more than one way to solve these problems. Good news, you have all those formulas sitting right there. You just have to know what works best for you and what you want to use. Okay, so other P scales. The P in pH tells us to take the negative log of something. So don't freak out anytime it says pH, pKa, pOH. That just means whatever it is, take the negative log of it. So one of the things you'll notice, we have this Kw here. Well, if something said find the pKw, what that means is take the negative log of the Kw. And so just some examples here. POH is the negative log of the concentration of OH minus. pKw is the negative log of the product ion constant for water, and so on and so forth. So just be aware that, if you see that small lowercase p in front of anything, it really just means take the negative log of that quantity. All right, so because the concentration of hydronium ions times the concentration of hydroxide ions at 25 degrees Celsius equals 1 times 10 to the negative 14th. If we take the negative log of that equation, what we come up with is the negative log of hydronium ion plus the negative log of the concentration of hydroxide ion equals the negative log of Kw. Now, the negative log of 1 times 10 to the negative 14th is 14. That's where the pH and POH scale come from. So pH plus POH always should add up to 14. And see, there are tons of patterns here. It just takes time to see them. All right, let's take a look at one more type of problem. Okay, so for this one, we have a pH of 9.18, and we're asked to calculate the concentration of OH. Now you have all these wonderful formulas, and right away, your eyes might get drawn maybe to this equation right here. So if we take 14 minus 9.18, we get about 4.82. So then the question is, and that's our POH, the question is, how do I take that, plug it in here, and find the concentration of hydroxide? So in your calculator, first of all, we're going to take the opposite of 4.82. So we're going to take negative 4.82. And on your calculator above the log button, you probably have a 10 to the x. On mine, I have to hit shift and then log to get the 10 to the x. If you do that, you come up with 1.5 times 10 to the negative fifth. So take a minute, see if you can figure that out. But there's also some other ways that you can actually calculate concentration of hydroxide ion. And one of them is by using this as well. So there's a lot of different ways. Figure out what works for you, and let me know if you can't get that answer. Okay, last thing I want to talk about, ways that we measure pH. There's a couple different ways. One is with pH meters. So you can see in this picture, we've got something that's a basic solution. That's Phillips milk of magnesia. And then we also have indicators, and indicators change color when there is a change in pH. So there are certain indicators that you choose to change that will change color when you're looking at a certain change in pH. And so you'll choose indicators that will change color when you want them to. I think that's it for now. We will continue this later.